Welcome to the wonderful world of physics 104B. This is chapter 22, section 2, calculating potential difference. Just as a reminder from a previous section, when we talk about the potential difference between points A and B, you can think of it as the change in potential energy as a charge moves from A to B, divided by whatever that charge is. And that equals the negative integral integrated between A and B of the electric field vector E dotted with dr. So let's think about, on the left, this picture, a simple case of a positive point charge, and it's got the electric field lines pointing away from it radially. And I want to think about the voltage difference between A and B, or the potential difference between point A and point B. And coming from a point charge, the electric field is kq divided by r squared times that r hat unit vector. We could also think about a negative charge, which is the same scenario, but the electric field lines point inward. And we want to calculate the potential difference between points A and B in the vicinity of a single point charge. Now, thinking about it qualitatively, a positive test charge goes downhill, meaning going to the lower potential. So in the diagrams, on the diagram on the left, going from A to B, a positive test charge will automatically go. It'll be pushed by the electric field from A to B. And on the left diagram, it'll be automatically pushed from B to A. So on the right diagram with the negative charge, where my pointer's at, you can think of going from A to B as being uphill for a positive charge. It wants to go towards the negative, and so it has to, if it goes from A to B, it's going against the way it's being forced. All right, so let's think about the potential difference between A and B. That's the voltage at B minus the voltage at A, and that equals, as we see at the equation at the very top of the page, the negative integral from, we'll say, these distances, RA to RB of E dotted with dr. And electric field from a point charge, we've seen earlier, is kq over r squared. And so the electric field is kq over r squared r hat dotted with dr. Now that dr vector, you can think is r hat, because it's in that direction, times dr. Think of r hat as the unit vector pointing in that direction, and dr as being the magnitude of it. So when we take this dot product right here, there's certainly the kq over r squared, but think about that dot product, r hat dotted with r hat dr becomes, you can see in this line right here, r hat dotted with r hat, a vector dotted with itself is equal to, well, that's just going to be the magnitude, in this case 1. And we're left with the dr. And you can see just some basics of dot producting over here in the green. You have r hat and r hat. R hat dot r hat is magnitude r times magnitude r times cosine theta. But remember, in this case, r is 1. So that's, and cosine theta is, well, cosine of 0 degrees then is 1. So in the end, we're left with just that dr. Well, as we continue taking the integral, we'll throw the kq out to the side, and remember there's still a negative sign there. So we're taking the integral of r to the negative 2 dr, and that becomes negative 1 over r in the integral. So in the end, the voltage difference between points A and B from a point charge, as you see in the diagrams up above, is kq times 1 over rb minus 1 over ra. And remember that K is, in MKS units, 8.9876 times 10 to the 9th. So a quick example, let's say we have a charge of positive 1.1 repeating times 10 to the negative 10 coulombs. And I pick that simply so that when you multiply it with K, it becomes 1, just to make the arithmetic easy. And so the voltage difference between A and B is KQ, which is just we're gonna say 1, over and we see the difference of the reciprocals of the distances. Well, let's say we want to go from 0.5 meters away from the charge to 1 meter away from the charge. Now this is going to lower potential. It's going downhill for a positive charge. So we plug in those numbers, 1 over 1 minus 1 over 0.5, and we get negative 1 volts. Now let's say we have a negative charge, negative 1.1 times 10 to the negative 10 coulombs. And what that means when we plug in the numbers, we want to go from a close distance to a far distance. So from 0.5 to 1 meters, well, that's going to be an increase of 1 volt if you do the math. And it's going to higher potential. And higher potential, think of it as going uphill for a positive charge. And just to remind you, electric field lines always point in the direction of decreasing potential. Let's talk about the zero of potential. We came across this in first semester when we were talking about gravitational potential energy. Remember that with gravitational potential energy, before we learned about that G can change, just when early on in the semester when we had G being a constant 9.8, we had potential energy as mg times the height. But it was really difference in potential energy is mg times a difference in height above some arbitrary 0 point. And so we could take the zero of gravitational potential energy. It might be the ground. It might be the tabletop on which you're doing an experiment. It might be the floor that you're doing an experiment on, but you arbitrarily call it 0. Well, our 0 for potential energy in practical application could be the Earth itself. We often refer electrically to the Earth as ground. It could be a car's metal frame. For maybe when we talk about grounding jump cables, you attach one to the metal frame. For an isolated charge, we're going to do what's most convenient mathematically. We will take the 0 potential to be an infinite distance away. So we can say the difference in potential between A and B is kq times 1 over rb minus 1 over ra. And let's take ra as infinite distance. So that term 1 over ra will go to 0. And so then we'll be able to find the potential at B without explicitly having to refer to the potential at B above a particular point A. It's implied the potential above our arbitrary 0, which is an infinite distance away. So that equation becomes the difference, the voltage difference between A and B is simply kq over rb, which means when we want to find the voltage or the electric potential at a certain point, and again, we are specifically talking about a distance from some isolated point charge, we say that the voltage of some distance r is kq over r, where q is that charge, k of course is the Coulomb constant, and r is your distance. Now, like an example I did earlier in this video, let's let Q be negative 1.1 times 10 to the negative 10 coulombs. Therefore, KQ is negative 1. And you can see I've done the calculations here. Here's our negative charge. If you plug in the values at 1 centimeter away, you've got negative 100 volts. At 2 centimeters, negative 50 volts. Keeping on plugging in the numbers at 5 centimeters, negative 20 volts. 10 centimeters, negative 10 volts. And you can see every time I double the distance, the voltage gets cut in half. And so we go out to 20 centimeters and it's negative 5 volts. Off the page, you go out to 40 centimeters, it's negative 2.5 volts. So it slowly is going to increase going up to 0. But when will it actually be 0? Well, at an infinite distance. Here is example 22.3 in the book. It says, the Hall of Electricity at the Boston Museum of Science contains a large Van de Graaff generator, a device that builds up charge on a metal sphere. The sphere has radius of 2.30 meters and develops a charge of 640 microcoulombs. Considering this to be a single isolated sphere, find A, the potential at its surface, B, the work needed to bring a proton from infinity to the sphere's surface, and C, the potential difference between the sphere's surface and a point 2r from its center. All right, so here's what's written out. We want to know, again, A asks, what is the potential at the surface? So I'll call it V of capital R, and you can see my picture there. Part B, the work needed to bring a proton from infinity to the sphere's surface. Okay, so from infinity to R. And question C, the potential difference between the sphere's surface and a point 2r from its center. So you can see in my picture from R, between R and 2r. And in chapter 21, which is a chapter I skipped, but one thing that was learned there is that we can treat this entire sphere as a point charge. So anything beyond the sphere, we'll just see that charge sphere as a point charge and the point located right at r equals 0. Well, then, treating it like a point charge, we can say V as a function of r is kq over r. And you can see my graph right here, and there's another one in the book. It does no sense to talk about what is the voltage prior to R within the sphere, because the analogy to a point charge kind of breaks down within the sphere. But we'll basically say the voltage starts right here, and then it will decrease asymptotically down to 0. So V of R is just kq over the radius r. And we already know the radius is 2.30 meters. We plug that in, and I hope you're doing this at home also, so you can see that you get the same values that I'm getting, but 2.50 megavolts. Part B asks, what is the work to move one elementary charge, a positive elementary charge, a proton, across that potential difference? Because it says from infinity to R. So if you're wondering, where do we get a potential difference from? Because in part A, all I said was the voltage at the surface is 2.50 megavolts. But remember where that comes from. That is actually the potential difference between that point and an infinite distance away. So in part B, if we're moving a proton from infinite distance to the surface, that means we are moving it across a potential difference of 2.50 megavolts. And so the work that we do is the change in potential energy, bringing it from A to B, which is Q times the voltage difference between A and B. So 1E times 2.50 megavolts, and that gives us 2.50 mega electron volts. And I wrote down here, why is it positive work? Or is it positive work? Yes. Because you think it's a positively charged sphere, so the proton is repelled. We have to do positive work to push it closer. We're moving it uphill. Part C asks, what is the voltage difference between 2R and R, between those distances? Well, we can just say kq over 2R minus kq over R. That becomes negative kq over 2R, or negative 1.25 megavolts. And the voltage is lower because we are moving away. Let's look at example 22.5, the dipole potential. It says an electric dipole consists of point charges plus and minus q, as you can see in the diagram, a distance 2a apart. Find the potential at an arbitrary point P and approximate for the case where the distance to P is large compared with the charge separation. So here's a picture that I've drawn with the necessary angles right there. There's a point P up there. So for several point charges, in this case only 2, we can add the voltages by superposition. So we can say that the voltage at P is, we'll take for the positive charge first, kq over that distance, which I've labeled R1, plus for the negative, k times negative q times R2. And this leg here is R2. Now, that's going to be kq, if we simplify that, times 1 over R1 minus 1 over R2. And that is going to be, if we combine those fractions, R2 minus R1 over R1, R2. Now, I've done a little bit of geometric approximation here, where right here, this purple bit that I'm tracing out right here, that's R2 minus R1, which is approximately, going from the geometry of some of these triangles, 2a times the cosine of theta, because that's a right triangle in there, and the hypotenuse is 2a, so this purple leg here is 2a times the cosine of theta. Now, if r is much, much greater than a, and r with no subscript is just the distance from the center point to P, then we can do an approximation that R1 times R2, if P is of sufficient distance away, R1 and R2 we can say are pretty much the same thing. Let's just roughly estimate that they're both R. It's a rough estimation, but that's why I've written here in purple, R1 times R2 is approximately R squared. Okay, so now with that in mind, this denominator that we found with the math, I'm just going to call R1 and R2 R squared with that approximation. And R2 minus R1 in the numerator, what you can see in the purple here, that's 2a cosine theta. So now if we let the dipole moment, that's P, we recognize that that is 2aq. You learned that in a previous chapter. That's what dipole moment is. We can consolidate some of this. We see a 2, an A, and a Q, and call the voltage at point P to be K times the dipole moment times cosine theta over R squared. So here you have this simplified diagram where you have a positive charge and negative charge, some distance between them, and P is just some distance R away. And if you look at that, what that means is that voltage is proportional to 1 over R squared. Now remember, for a point charge, voltage is proportional to 1 over R. We did some examples of that earlier in this video. But for a dipole, voltage is proportional to 1 over R squared, so it falls off more quickly. And by the way, when theta is 90 degrees, so it's straight perpendicular, V is 0 because the charges perfectly cancel out. We're going to look now at a continuous charge distribution, or a variety of continuous charge distributions. Now, when we think about a continuous distribution of charge, we're going to consider it to be made of infinitely many little charges. We'll call them dq's, each acting like a point charge. And they each contribute a little bit of voltage, we'll call it dV, to the total potential. So that little bit of voltage, dV, from a little tiny point charge is K dqr, or K dq over R. So the entire voltage coming from this continuous charge distribution is the sum of all those little dVs, the integral of dV. So that's the integral of K dq over R. K is a constant, we'll throw it out to the left, so K times the integral of dq over R. So this is the main equation that we're going to use to think about these continuous charge distributions. Such as, example 22.6, we're looking at the potential of a charged ring. You see the picture there, you can also see in the book. A total charge of capital Q is distributed uniformly around a thin ring of radius A. Find the potential on the ring's axis. So here's the picture that I've drawn. Somewhere along that axis at some arbitrary point P. Notice the geometry here. I've drawn a little charge dq. The ring has a radius of A, and we are some distance x away from it. What's going to be important is the distance, not from the center of the ring, but the distance from our point to the little charge. And by Pythagorean theorem, that's r equals square root of x squared plus a squared. Notice also that because it's a ring, R is the same for all of the charges around the ring. So I've drawn it at the top, but whether it's here on the side or here on the bottom, that's going to be a constant R. which is great because that's one more constant that we can factor out to the left of our integral. Let's start with the voltage, or the electric potential, as a function of x is k times integral dq over r. But now we get to throw r out to the side because it's constant for all these different points. And we're left with k over r times the integral of dq. A very easy integral to do. The sum of all the dq's is just capital Q. So we have kq over r. Now, with the dimensions given, we actually aren't given what r is, but we are given the radius of the ring, and we want to know with respect to the distance along that radius. So it's more convenient actually to write it not as kq over r, but as kq over square root of x squared plus a squared. And then we can assess this and think, for a large distance, if x is much, much bigger than the ring, imagine we're zooming out far enough, maybe so it's so far away we can't even see that it's a ring. Well, then we would just observe it to be a point that has a charge q. So a test of this equation to see does it actually make sense at large distances is to see that if a is very, very tiny, we're left with just kq over x, and that is, as we know, the voltage or the electric potential from a point charge. Let's take a look at problem number 55 in the back of the chapter. It says a thin ring of radius r carries a charge 3q distributed uniformly over 3/4 of its circumference. And you can see that in the picture, the green area. And negative q over the rest. Find the potential at the ring's center. So, looks kind of complicated maybe. So 3q over here and negative q there. What we're going to do is take the sum of all the little dv's. So voltage is the integral of all the dv's, and that equals kr dq. And what we can do is think about what we got out of the last example with a charged ring along the axis. And you think this does apply because the center of the ring is on the axis. It's just where x equals 0. So what we're actually going to use is the result from the previous lesson that says, so it's kq over square root of x squared plus a squared. And doing the integral, all the little point charges, it turns out that they don't need to be uniformly distributed. When you add all the little charges, some of them being positive, some of them being negative, it comes out to be k times, and the sum of all the dq's is the total q. So 3q plus negative q, that ring has a total charge of 2q. And x equals 0, so that part goes away, and we're left with the square root of a squared, which is, so a is what we used in the example for the radius of the ring, but here in problem 55 it's calling the radius r, so let's just call a r. And so we have the voltage is k times the total charge 2q over r. Let's now look at example 22.7 that's going to build on the last example of a ring. This is a charged disk. It says a charged disk of radius a carries a charge q distributed uniformly over its surface. Find the potential at a point P on the disk axis, a distance x from the disk. So this is very much like the ring problem. In fact, what we're going to do is think of that disk as many, many infinitesimally thin rings. So all of the little dq's we should see are not equidistant to P. That worked when it was a ring, but now you think there's a charge here, a charge here, a charge here. They're not all the same distance from P. Well, what we can do is divide the disk into little rings. So we'll say that the voltage at some distance x is the integral of all the little voltages, dV, and that equals And what we're going to do is take a bunch of those rings. So all the little dv's are k, and I've already thrown the k out to the side, times dq over square root of x squared plus r squared. Now x, I haven't drawn the diagram, but x is the distance along the axis, so it's where p is at. X squared plus the radius r squared, so that's going to be the distance to the charge from the charge to point P. Now, we're going to get this integral in terms of dr. We don't want to integrate over charge. We want to integrate over distance, over space. So using a technique that we learned first semester, we can say that the area of a single ring over the area of the disk is equal to the charge of that ring divided by the entire charge. And then that equation becomes for the ring area. Now notice in the diagram, little r refers to the radius of a particular ring. So the ring area is, well, if you imagine taking that ring and laying it out, stretching it out, it makes a rectangle. And the area of it is base times height of that rectangle. So the base of it, or the length, is the circumference of the ring, 2 pi r, times its height, the thickness, is dr. So the area of that ring, if we stretch it out like a rectangle, we see is 2 pi r dr, divided by the disk area, the entire disk, and that's pi a squared. And that equals dq over the big charge q. That leads us, when we simplify this, the pi's go away, various things divide out, and we're left with dq is 2qr over a squared dr. Perfect. Now we can take that value of dq and plug it into our integral. And then we won't be integrating over dq, but rather dr. So when we plug what I've got here, where you can see by my marker what's written in the green dq, and we plug it into the integral up here, we get that the electric potential difference is the integral of, and we still have, well, k thrown to the left of the integral, from 0 to a, of 2qr over a squared, 1 over x squared plus r squared, square rooted dr. Now let's work through that integral. We can take the big Q and the a squared, throw them out to the side. We're left with the integral of r over x squared plus r squared dr. That is not an integral that I expect you to know, and this is where it's good to own a good table of integrals, to be able to look in a table and see what is this integral. Well, it comes out, here is down below, you can see when I look up in my table of integrals, it is x dx. Now keep in mind, in a table of integrals, you're not going to get the letters of your choice or the letters that happen to appear in the equation you're working with. It'll tend to be the letter x as the variable that's integrated over. So the integral of x dx over square root of x squared plus or minus a squared is square root of x squared plus or minus a squared. And so you go with the plus or minus accordingly. So you have to make a little conversion in your head. In our integral, the r is the x here, and in our integral, the x is the a here. So you do that conversion. What you end up with is it's 2kq over a squared, and the integral becomes square root of r squared plus x squared, integrating from 0 to a. So we put those together, we integrate, and we get what you see down on the bottom of the screen. And then in the end, simplifying a bit, that minus square root of x squared actually becomes minus the absolute value of x. So this is the final result down below. And that is the end of section 22-2. Have a great day.